Okay. So, that is why the voltage drop, that equation actually it is approximate, right. Actually this is your I A into R 1, only this term we are writing, plus I B into R 1 plus R 2 plus I C into R 1 plus R 2 plus R 3, right. But this magnitude, this other term, this term we have not considered here. Generally in a distribution system, this R values are higher, then a ratio of R by X always greater than 1, right. So, that is why these values are much smaller, that is why we did not consider, but exact computation later I will show you. We have made it using calculating voltages V A, V B, V C, everything, but that is why approximate calculation, that that if you want to make approximate voltage drop. So, this will be the formula, V D will be for that example it will be your I A, this is the current I A going 30 ampere into R 1, then plus your I B into R 1 plus R 2, then I C into R 1 plus R 2 plus R 3, whatever it is coming here from this derivation, right. So, that is why that approximate method, actually we do not use that complex term will be very small. So, total, that means total voltage drop 14.264 volt means that at distribution, this is taking for 240 volt, just for your understanding. So, this point voltage is actually 240 volt, the secondary side of the transformer. That means, at the total voltage drop is 14.264 means that the tail end of the feeder, that means here at point C, the voltage will be 240, because it is given 240 minus 14.264, that will be the voltage at this point, right. So, that is the total voltage drop of the line, that is why it is in per unit, it will be 0.594 per unit, right. This is the total voltage drop, that is at the end of the feeder, the voltage will be actually 240 minus this one, that is at point C, right. So, that, and this way next one you have to compute the real power. The real power per phase for each load can be calculated, P is equal to V I cos theta, right. So, it is per phase only we are computing. So, P A plus P B plus P C. So, V I for first load it is V I cos theta, it is 1, second load I is 20 ampere, V I cos theta is 0.5 given, everything is given, your everything is given, unity power factor, lagging power factor, for this one all data are given. Based on that only we are putting, and then V is 240 all the time, 50 into 0.9, right. So, this way the total power will be 7.2 plus 2.4 plus 10.8 kilowatt, that is 20.4 kilowatt per phase. This is approximate one, this is approximate one. Why? That everywhere we are taking the voltage is 240 volt, right. This is approximate one, that every node voltage is actually 240 volt, that is approximate one, right. So, but if you calculate voltage it will be different, right. Similarly, Q is equal to in general V I sin theta, that is Q A plus Q B plus Q C, that will be 240 into 30 into your cos theta 1 sin theta 0 plus 240 into 20 the current into sin theta 0.866 plus 240 into 50 the current into sin theta 0.436. If you compute, it is 9.389 kilovar per phase, right. Now, if you neglect the loss, the kVA output of the distribution transformer, suppose loss is neglected, no loss is there. So, this is my P and this is my Q, right. Therefore, S is equal to root over P square plus Q square. So, P is coming 20.4 and Q is coming 9.3. These are all these calculations actually and made on the rated value, because we have to plan the distribution transformer or what you call rating. But if you go for calculation, you will find V A, V B, V C, the voltages are less than 240, but for the planning stage and approximate one will be all voltages are taken same, right. So, that means it is coming 22.457 kVA per phase, right. Therefore, the total kVA output of the distribution transformer is, it is 3 phase. So, 3 into 22.457, therefore, 67.37 kVA, right. Hence, the load power factor of the distribution transformer will be cos theta is equal to P upon S, P is 20.4, S is equal to 22.457. So, it is coming 0.908 lagging power factor, right. So, now branch loss calculation, these are the current given at this your what you call in this diagram, it is this current, actually this current is I A this current is IA, this is IB and this is IC at node thing, right. Here I am not putting IA, IB, IC, but understandable, right. So, here it is IA is equal to 30 angle 0 because unity power factor it was, IB is equal to 20 angle minus 60 because power factor lagging 0.5. So, it is 10 minus j 17.32 ampere, and IC is equal to 50 angle minus 25.84 degree, that is 45 minus j 21.79 ampere, right. Therefore, first branch current I1 is equal to IA plus IB plus IC, right. So, this branch current I1, right, here I have used small I1, there should not be any confusion for you, better I should make it capital I1, right. So, I1 is equal to IA plus IB plus IC, because this branch current will be IA plus IB plus IC, sum it up all, right. So, if you IA, IB, IC you substitute, it will become 85 minus j 39.11 ampere, right. Next is, so that means I1 I make capital 1, there should not be any confusion, capital I1 is equal to, it will come 93.566 minus 24.7 ampere. Similarly, current in branch 2, actually I1 I2 means this branch, I should redraw this diagram, right, then things will be easier for you, better I should redraw. So, instead of spoiling this diagram, I am redrawing for you. Suppose you have a distribution transformer, right, these are your node, this is point A, point B, point C, this is A, this is B and this is C, this is O, right, this is your distribution transformer, right, and here the current is there, your IA is equal to, it is given 30 angle 0 because unity power factor, this is current B, it is your IB is given your 20, right, 20 magnitude and power factor is your, it is minus 60 degree ampere, right, and this is your IC, right, and this is your IC is given 50 and cos theta is equal to 0.9. So, it is minus 25.84 degree, right. This is actually your what you call that current IB, IC. So, this through this current flowing is I1, this is I2 and this is I3, right. That means, your just now we have seen no, I1 is equal to this is, that means your IA plus IB plus IC, I2 is equal to IB plus IC and I3 is equal to IC, right. So, this is the thing actually. So, whenever we are computing this one, right. So, this is your I1, I2 all have been shown and next this I2, right. So, this is your value of I2 is 10, similarly I2 is equal to IB, this is actually IB, this is actually IC, right. So, here it is capital, here you make capital, so that there should not be any confusion. So, it is IB and it is IC, if you add it will become 67.4877 angle minus 35.41 degree ampere, right, and I3 is equal to IC, right. So, make it capital, I3 is equal to IC. So, it is 50 angle minus 25.84 degree ampere, right. So, branch power loss, so it will be capital I1 square, capital I2 square and capital I3 square, right. So, all I1, I2 and I3 magnitude are known, R1, R2, R3 all values are known. So, put it here and if you simplify it will become 1.017 kilowatt per phase, right. This is your P loss. Similarly, for Q loss it will be, here I have written capital I1 square x1 plus capital I2 square x2 plus capital I3 square x3, right. So, Q loss will be substitute all the values of I1 and x1, x2, x3 everything. So, it will coming actually, this is var converted to kilovar, it is Q loss is 0.303 kilovar per phase, right. Therefore, real power output of the distribution transformer, that is say I am making PS dash, actually it should be P plus P loss, because load plus loss it has to supply. So, it is coming actually 20.4 plus 1.017 kilowatt per phase, that is 21.417 kilowatt per phase. Similarly, reactive power it will be Q plus Q loss, we already this P value earlier we got, this Q value earlier we got 9.389 plus 0.303 kilovar per phase. That means Qs dash is equal to 9.692 kilovar per phase. So, this is Ps dash and this is Qs dash, right. Therefore, kVA output of the distribution transformer is, so S dash is equal to root over Ps dash square plus Qs dash square. So, it is actually 21.417 square plus 9.692 square. So, kVA per phase, it is coming 23.5079 kVA per phase. So, for 3 phase transformer, if you multiply, it will be 70.52 kVA multiply by 3. Previously, we saw it is approximately 67, but that was loss ignored. But as soon as you have to you are considering the loss, it is coming 70.52 kVA. Therefore, power factor will be actually P by S dash. So, 20.4 divided by your this thing 23.5079. So, it is 0.867, but at substation power factor actually it is whatever we have taken the load, actually it will become your this what you call this Ps dash, it is 21.417. So, power factor at the substation instead of 20.4 load you should take 21.417, right. So, almost, so this value is based on this 20.4, but actually I have missed this one, actually it should have been 21.417. So, please compute it, it will be nearly 0.9, I do not have calculator here, but it will be nearly 0.9, right. So, and exact solution if you want, then for this your what you call for this node. So, VA actually substation voltage is 240 angle 0 minus your I1 Z1, this is I should make capital I1 Z1. So, I1 is known, Z1 is also known, everything is given, all data, all parameters, everything is here, all this is Z1, this is Z2, this is Z3, right, Z1, Z2, Z3. So, if you simplify, you will find VA will become 235.36 angle 0.27 degree volt. You check all the calculations, I hope all these calculations are correct, but you should check it. Similarly, VB is equal to VA minus your capital I2, I2 Z2. If you simplify, it will become VB is equal to 229 point your what you call 11 angle 0.48 degree volt, right. Similarly, VC is equal to VB minus I3 Z3. You substitute this VB value, I3 Z3 value, you will get actually 225.75 angle 0.7 degree volt, right. So, all the node voltage at A, B, C you will get this much, but earlier that means end point voltage was 225.75. So, in substation voltage was 240.00 and this is 225.75. If you subtract here, right. So, it will be 14.25 volt, right. So, this one we got using this your what you call using that your voltage calculation, because it is no iteration here, because all currents are known to you, and earlier for voltage drop method, voltage drop how much we have got 14.264, 14.264. So, here it is coming 14.25 and ultimately here it is coming 14.264. This is the approximate method, this is that approximate method we got 14.264 and it is 14.25. So, it is as accurate as anything, right, for this small system. So, that is why that approximate formula is used for distribution system, right. With this, that some idea I have given you regarding approximate method for distribution system analysis, right. After this, what will happen, we will move to your what you call application of capacitor to distribution system. Here things will be interesting, but you have to understand many things. Before proceeding all the basic, one or two things I would like to explain at the beginning itself, right. Although whatever problem we will consider in that in this course, that will be as far as possible classroom your what you call that classroom exercise. So, suppose you have a distribution network, look, you just try to understand first that it will be application of capacitor to distribution system. This will be the headline, that application of capacitor to distribution system. I will come to that all this thing later, but before that certain things you have to understand. Although bigger problem cannot be taken, but you should make your concept clear at here itself, right. So, suppose this is the thing, suppose you have first thing the concept of the lagging leading load, then little bit of because it is a capacitor application problem, but little bit of distributed generation also, how it can be incorporated, some ideas, right. For example, suppose you take any node, right, you take any node, for example, you take any node, suppose this is your some node, right, here you have a load, here you have a load, this is your load, right, or I can put it here, this is your load, right, and this is some node, some node I say I, right. Suppose you have load here is suppose PL plus JQL, right, this is the load. Now, when this you have to understand, when QL, understand means simple thing, you have to keep it, when QL greater than 0, I mean QL is positive, but look, the load is absorbing power, arrow direction is downwards, arrow direction is downward means the load is absorbing power. So, when QL greater than 0, it is actually lagging load, right. So, and when QL equal to 0, then QL 0 means it is real load, that is unity power factor load. So, in short we call it is UPF load, that is your unity power factor load, right. And when QL is negative, that is QL is negative less than 0, so it is leading power factor load, right. So, this is lagging power factor load, this is unity, when QL is positive, it is lagging power factor load, when QL is 0, it is unity power factor load, and when QL negative, it is leading power factor load, right. So, this is for the load point of view, right. Now, suppose I am showing, suppose another thing is there, suppose you have another node, say node I, for example, some node, suppose you have a source, right, suppose you have a source, its source may be renewable base, whatever it is, it suppose you are connecting it to AC network, right. So, whatever it is, it has to be converted to even in DC also, for example, solar PV, that you are converting by using inverter to the AC thing, right. But our objective is only thing that if it is a power being injected into the network or any bus, if it is suppose this is PG and this is plus JQG, that means arrow is this direction, arrow is upward, that means it is injecting power, right. In that case, if here QG greater than 0, that means it is lagging generation, right. So, or in the instead of if it is a distributed generation, it will be lagging DG, right. So, lagging generation, only both are same, whatever I write both are same, only directions are different, here power being injected, here power being absorbed, right. So, this is lagging generation, when QG is equal to 0, it is unity power factor thing, right. So, that means there is no reactive power, only real power being injected. So, it is your unity power factor generation, right. Similarly, when QG negative, it is actually leading, it is lagging power factor generation, it is unity power factor generation, and this is leading power factor generation, right. So, both the cases things are same, here it is QL greater than 0 less than, only thing is that in the case of load it is absorbing power, in the case of generation it is injecting power, it is power supplying to the network, right. So, now if it is so, suppose you have a common node where P load and generation both are there, right. If it is a common node, if load and generation both are there, suppose this is your bus bar, right, say bus I, say this is your load, this is your PL plus JQL, this is the load, right, and this is same bus bar, suppose generation is connected, right, this is PG plus JQ, this is downward, this is upward. Now, what will be a resultant of these two? So, resultant of these two in the downward direction, right. Suppose this is bus I and resultant should be in the downward direction, it will be like this, PL minus PG, because it is upward, we are taking downward. So, it will be negative sign plus J your QL minus QG, right. So, this is that your resultant, right. So, question is that PL minus PG may be negative, does not matter, it does not mean that it will be positive, it will be negative. QL minus QG also it may become negative, it does not matter, positive or negative, this one also positive or negative, it does not matter, right. So, this is actually what you call in the case of your some generation, some power is injected. For example, this is a distributed generation DG, the power being injected. So, this is the concept of power injection in the load flow studies, or any small thing you take, you have to take like this. Now, instead of your what you call DG, suppose instead of, if it is a capacitor, if it is a shunt capacitor, say suppose this is your load, this is your load, this is a node I say, this is your PL plus JQL, and this is your capacitor, this is your capacitor. So, it is JQC being in your JQC. So, QC is being injected, right. So, resultant of this one, this is bus I, right. In the direction it will be PL only, here no question of real power, right. So, it is PL plus in this direction QL minus QC, that means that reactive power actually is getting reduced, but PL will remain same. That means, in this expression if PG is 0, in this expression if PG is 0 and QG replaced by QC, you will get this one. So, that means, this is the your what you call that load flow studies. If you consider a DG, the concept will be like this, if it is a capacitor it will be like this. So, that is why before your what you call going to the application of capacitor, this much I told you that what will be the concept. Second thing is suppose you have a network, take radial network only, take one more node, first you understand all this, later you will find we have taken all the simplest thing from the classroom point of view, right. Suppose this is your substation, this is bus 2, bus 3, bus 4, bus 5, there are 6 bus, right. So, as our objective in our capacitor, suppose we have connected a capacitor here, right. So, QC is being injected, JQC we are making it, right, and everywhere the load is there, everywhere. This is your PL2 plus JQL2, here also load is there, PL3 plus JQL3, load is there, here also load is there, PL4 plus JQL4, along with that capacitor is connected at node 4. So, here also load is there, PL5 plus JQL5, and here also PL6 plus JQL6, it is load is there, right. So, in that case this is then what will be the effect of, first you have to understand what is the effect of capacitor. Now, if you think, forget about losses, all there are 5 branches 1, 2, 3, 4, 5, suppose there are 5 branches, you forget about the branch losses, say there is no branch loss, right. Now, if you think that what will be the electrical equivalent, you take this is branch 1, this is say branch 2, no, branch 3, branch 4, and this is branch 5, right. There are 5 branches. So, if you take electrical equivalent of branch 1, then what is P2, right, and what is Q2? P2 will be for branch 1 only, electrical equivalent of branch 1, the total load fed through the node P2 will be, you will be PL2 plus PL3 plus PL4 plus PL5 plus PL6, right, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6 is P2. Now, what will be Q2? Q2 will be first QL2 plus QL3 plus come to here QL4, right. I told you that just now I told you that everywhere QC is connected will PL4 plus JQL4 QL minus QC, just I told that it will be PL plus JQL minus QC. So, here that resultant reactive load in the direction of the load, right, in the direction of the load, it will be actually put here QC4, that is better, at node 4 QC4. So, it will be QL4 minus QC4. So, it will be QL4 minus QC4, right, plus your QL5 plus QL6. So, here the change, right, all the basically QL2, QL3, QL4, QL5, QL6, but this being injected. So, it will be your QC4. Similarly, first you have to understand, similarly if you come to your P3, it will be again PL3 plus PL4 plus PL5 plus PL6. So, I am not writing P3, my objective is to Q, because cap Q is being injected. Similarly, P4 will be PL4, PL5, PL6, P5 will be PL5, PL6 and P6 will be PL6. This is understandable. Now, if you write, I am writing only Q, Q3 will be again QL3, only this one will be dropped, QL3 plus QL4 minus QC4 plus QL5 plus QL6, right, that is Q3. If you write Q3 Q4, that is your Q4, so this term will be dropped, this term will be dropped, it will be QL4 minus QC4 plus QL5 plus QL6, right. So, up to Q4 it is fine, up to Q4 it is fine. Now, next is if you write Q5, what is Q5? Then Q5 will be these two term for the node 4, this will be dropped, is equal to QL5 plus QL6, and Q6 will be QL6, right. Now, if you look into that when this capacitors that connected at node 4, up to node 4 the effect of QC is there, up to node 4 Q3 also function of QC4, QT also function of your QC4, Q4 also function of QC4, right. But as soon as you are coming to 5, you are leaving this, node, you are leaving this node. That means, your Q5 is equal to QL5 plus QL6, because capacitor is behind this node, right, not ahead of that, and Q6 will be simply QL6. That means, what does it mean? That means that whenever you connect a capacitor, right, this capacitive, I mean intuitively or philosophically you can tell this capacitor when you connect, it is QC means it is also injecting current here IC, it is also injecting current here IC, say I am just putting IC, say this injecting current IC. That means, from the connected node, right, from the connect, because all these things, these 2, 3, 4, all this node from this point it is coming towards the source side, right, other side it is no effect is there, no effect is, that means this thing actually from connecting node, this capacitive thing is flowing to this side, its current is flowing to this side, right. So, I mean this is the basic philosophy, that means this side 5 and 6 not affected by this capacitor, that means whatever branch losses will reduce due to capacitor placement, because whenever you use your shunt capacitor, right, and so first is series capacitor, if you put, we will come to that for a capacitor application. Series capacitor actually main purpose is to increase the voltage magnitude, right, of the each node, that is the function of series capacitor, and as the voltage is increased, so power loss is inversely proportional to the square of the voltage magnitude. We have seen power loss of branch, that is your R into P square plus Q square upon V 2 square. So, inversely proportional to the square of the voltage magnitude. So, though your what you call though because but series capacitor purpose is that it should increase the voltage magnitude, right, and though not much, because of the improvement of the voltage magnitude, to some extent power loss also will reduce. And in the case of shunt capacitor, it is that main purpose is that your primary objective is that it should reduce the power loss, right, it should reduce the power loss, but at the same time that your what you call that voltage also being improved, little bit improved. So, it effect is there also for loss reduction, but here for this branch and this branch there is no effect is coming for the capacitor, when you are computing P5 or P6 there is no effect is coming. Therefore, in the branch case that will be there will be no power loss in these two branch due to capacitive current, only this branch power loss reduction will be there because of the capacitor placement, though not much, voltage will be improved, right, because of the because all these 2, 3, 4 node voltage will improve, hence 5 and 6 also voltage will improve. Due to the voltage improvement, there will be a little bit of loss reduction in branch 4 and branch 5. So, this is the philosophy. Now, when I am making this your what you call this this is the current, suppose if I make that this is the IC current flowing like this. So, if you take the diagram, same diagram, right, just hold on, if you take the same diagram, suppose this is your 1, this is 2, 3, 4, 5 and 6, there are 6 nodes, 1, 2, 3, 4, 5, the same 6 nodes are there. So, capacitor is connected at node 5, this is the node, right. So, this is branch 1, branch 2, branch 3. So, current through the branch, say it is ID1 plus j IQ1, say real component of the current and imaginary component of the current. This branch current, say I2 is equal to say ID2 plus j IQ2. If it is lagging, IQ2 will be negative, does not matter, and this branch say current is ID3 plus j IQ3, right, and this branch say branch 4 ID4 plus j IQ4, and this branch say it is ID5 plus j IQ5. This is in terms of real and imaginary, and this capacitor current is IC. I told you this current will be moving like this. So, ultimately this branch effective current will be ID3 plus j IQ3 minus IC4. This node, this is your IC, I can make it IC4, right, because this current will be flowing this. When this current will be here, this current actually will become ID2 plus j IQ2 minus IC4, right. When it is coming here, this current will become ID1 plus j IQ1 minus IC4. This will be the your trend, right, because you have connected. If IC4 is 0, it will remain as it is. That means, this IC current actually flowing like this, flowing like this, flowing like this toward the source, but this side there is no effect of capacitor. So, using the load I told you up to node 4 it will be, it is effective, but when it is coming here, this side actually nothing, it is from the connecting node to the source. But as you are moving to the source, everywhere load is there, everywhere load is there, everywhere load is there. That means, your this at the branch 1 ID1 and IQ1 will be higher. Therefore, IQ1 minus IC4 difference will be your higher, but when you moving here, difference of IQ2 minus IC4 further will be your, here it may be higher, but IQ2 will be less, because some IQ2 will go to the load. Therefore, some current will go to the load, therefore, it will decrease, but when it is very close to the capacitor, this IQ3 minus I, the difference will be less. That means, whenever you are connecting a capacitor at any network, right, the effect is local. That means, that branches which are very close to for distribution system, very close to the capaciting connecting point, their loss reduction will be higher, right. As you are moving, but this is small network, as if you take a large network, as you are moving toward this difference actually there will be not much decrease, right. So, loss reduction will be less, but capacitor in the vicinity of the connection of the capacitor, shunt capacitor, the loss reduction will be more, right. So, this is something, because just basic thing, before we will take simple thing, because in the classroom exercise we cannot show all this without in the help of computer, right, because we need large network we have to show, but only thing keep it in your mind that capacitor, shunt capacitors effect actually it is local. Local means in the nearby region power loss reduction will be maximum, but as you are moving far away, the in terms of percentage loss reduction will be low, and main purpose of shunt capacitor is that it will reduce the power loss, right, and though not much, it improves the voltage magnitude, because every branch there will be less current, therefore, less voltage drop, right. Therefore, what you call to some extent voltage also will improve. I will take one small example in detail when we will go, right, but these are the basic philosophy. Thank you very much.